In this problem, we're asked to find all zeros for this given polynomial. And when we say all zeros, we mean the real zeros as well as the complex zeros. Now, we're not given any other information to go on, so in order to start the process, we really could use some help in finding at least one real zero. So what we're going to do is take a look at a graph of this function, and hopefully we'll see an x-intercept. So what I've done is I've gone ahead and put x to the third plus 2x squared plus 10x minus 136 into a graphing utility, and now we'll insert the graph. Now I also adjusted the viewing windows to go from -5 to 5 on both the x and the y, because with a y-intercept of -136, this graph was rather large. But the main thing we're interested in is where does this graph cross the x-axis, and as we can see, it crosses at 4. So what that tells us is that we do know one zero, namely 4. So we can now proceed by putting 4 in the box of a synthetic division and divide 4 into this polynomial. So the coefficients would be 1, 2, 10, and -136. Okay, so we leave some space and draw a line. We pull down the first number, 1, to get started, and we begin our synthetic division. So we'll take 4 times 1, 4, put it in the next line, or next column above the line, and then add down. So 2 plus 4 gives me 6. And then repeat that process. So 4 times 6 makes 24. Adding 10 and 24 gets 34. Now 4 times 34 gets me 136, and lo and behold, those add to 0, which means we don't have any remainder. This divides, the 0 of 4 divides evenly. So our 1 for the polynomial corresponded to an x to the third. So we know that this 1 corresponds to an x to the second, plus 6x plus 34 in descending order. So the factor from the 0 of 4 is x minus 4, and the remaining factor is 1x squared, or just x squared, plus 6x plus 34. So now we need to see if we can break down the second factor there, the x squared plus 6x plus 34. If we think about multiples of 34 to see if it factors, 1 and 34 certainly don't add or subtract to give us our 6 in the middle. 2 goes into 34 17 times, and again that doesn't add or subtract. And those are the only factors of 34, so it looks like that's not going to factor. But we're going to take the x squared plus 6x plus 34, set it equal to 0, and use the quadratic formula. So just to have it in front of us, x equals the opposite of b, plus or minus square root b squared minus 4ac, all over 2a. And for our problem, a is the assumed coefficient of the x squared, b is the positive 6, coefficient of the x, and c is the positive 34. So carefully putting the numbers into the formula, the opposite of b would be -6 plus or minus square root b squared, 6 squared gets us 36, minus 4 times the a number 1 times the c number 34, we'll come back and do that computation, all over 2 times the a number, 2 times 1, or just 2. So now we'll begin working on this by beginning with reducing what's under the radical. So we have -6 plus or minus square root. We'll keep the 36 for now and multiply the -4 times 1 times 34. So there's only one minus, so we have a minus, and then 4 times 1 is 4 times 34 is 136. still all divided by 2. So continuing on, we will now take a look at what's under the radical. So negative 6 plus or minus square root. 36 minus 136 is negative 100, all divided by 2. Now if we take our negative 100 under the square root and go to the side, since 100 is a perfect square, we can break that up to be the square root of 100 times the square root of negative 1. And square root of 100 comes out as a 10, and square root of negative 1 is defined as the imaginary unit I. So now we have negative 6 plus or minus, replacing the square root of negative 100 with 10i. And then dividing by 10, since they're complex, I'm going to separate them and reduce them separately. So negative 6 divided by 2 gets me negative 3, plus or minus 10 divided by 5. My brain just works faster than my hands. So 10 divided by 2 gives me 5i. So remember, we were asked to find all the zeros, both real and complex, for this polynomial. So we found from the graph that we had a 0 of 4, that was our real 0, and then 2 complex zeros, negative 3 plus 5i, and negative 3 minus 5i. And remember, the real zeros we can see as x-intercepts on the graph, whether they're rational or irrational, we can see them crossing the x-axis. But the complex zeros are truly imaginary. We don't see them crossing the x-axis. So we have accomplished our goal and found that all the zeros, again keep in mind it was a third degree polynomial, so there are exactly 3 zeros of 4, negative 3 plus 5i, and negative 3 minus 5i.